1 2 1 2 1 2 1 2 1 2. Woo!
So hello guys and welcome back to this one. We are going to be looking now at the Inorder Traversal Debugger 2 version, where we now see readily this Inorder Traversal in action, moving through the BST tree now in real time, and we see how at the end of the day we have a sorted list, but we see how the Inorder Traversal actually moves in recursive state. So basically that's what we are going to be looking at now, and yeah, hope you grasp the whole concept. So let's get into it. So we already instantiated the debugger tool, and let's see. So we already inside the function, right? And let's begin transversal. So we see here that, so let's see where the value of the tree we are at. So we are at 4 right now. So you can see our 3, 4 is the root. So we see our 4 right now. So we begin going down the tree. So we ask if root is none, return none. So root is not none. So we go to the left, right? So we go to the left. Now in the left, you see that our value has changed. Then it's now 2. We're now in the stack of 2, and right. So we are now in the stack of 1. Okay. So I think we are now in this in the okay. We are back to 1 after realizing that the left of 1 is a none. So we've printed out 1, and now we are on the right of 1. We could see that the stack we are still on is the value of 1. So if we click this, we get back to 2 after going down to the right, seeing that it is none, and then coming back to see that, and then finishing the function over here, and then going back up the stack to 2. Now we are going to go to the next bit, or that's printing out 2. So we could see here that we are 2 and printing it out. So we print it out. Okay. So we print it out, but we've also gone to the right 3 after printing it out. We go to the right 3 because that's where we have 3. So we can see that here, right? So these two, we are now at 3. Now at 3, we check if 3 is in a none. So we see obviously it's not a none. So we're going to go to the left of none. So if we step in, we see that our root is pointing to a none, right? So we know we've got a none, and then we are going to return none eventually. But yeah, we return none, and then we get back to 3, and then we print 3 out, and then we go to the right. I think if we step in again, we see here that we have a none, and we return that none subsequently. So we've done that, and now we are at the right, and now what, by clicking through, we get a full, we get our our 3 stack basically done, and we return back to 2, right? If we step through, so we return back to 2. 2 is also done because we have handled the right as well. So we click 2 and we get back to 4. So the same iteration is what we continue to the right, and we just step through that. You see 4, we print it out, we get to the right, now we get 6. Now we go to the left, we get 5. We go to the left again of 5, we've seen this none, so we print out 5, and we print out, and we go to the right, it's none, so we conclude on that stack, and we go back to 6. You can see that here. Now the same stuff again. You can see that the left returns none, so we continue our beat. We print out 6. Now we go to the right. The right is 7. Now this is the last bit. The left of 7 is none. The right of 7 is going to be none, but as of right now, we've already printed out 7. We could see that here illustrated. And then let's go down. So if you step into it, we get a none, or we step into it again, we return none, but that's the right of 7. As you see here, it's obviously a none, right? So yeah, we continue that bit, and we get back to 6. The right side of 6 has been exhausted, so we get back to 4, and boom, we are at the final bit of the solution. So Yeah, so if we look at the results here, we'll have 1, 2, 3, 4, 5, 6, and 7. So that's basically the bit of the whole in-order transversal using recursion, and that's what we handled here. And basically, next up, we are going to see how complexity now applies, um, why this complexity can then be, we can go ahead to optimize it, but also to see what the question was saying. Oh, please don't use recursion, or don't use stack, but we're going to get to stacks in a bit, but don't use recursion. So what did it mean there? Basically, what is now the optimization that can be gotten from using recursion, and maybe using something that is more like more efficient, right? So we see the complexity, we see what the improvement could be, and then we take it on from there. So see you on the next one. Muchas gracias. Bye.